In this video, we're going to take a look at rational functions. In particular, we're going to take a look at what they are, and then we're going to take a look at any restrictions that they might have on the domain and range. So first of all, rational functions are just two polynomials that are divided. So in fancy terms, you might have a rational function, which is h of x here, and that is going to be a fraction where you have a polynomial on the top and a polynomial on the bottom. So the numerator and the denominator are both polynomials themselves. An example of this might look like this one, where you have the polynomial x plus 5 in the numerator and the polynomial x squared plus 3x minus 4. Now, one of the first things we might want to talk about on something like this is what might the domain be? So you need to know a little bit about fractions or remember something about fractions. There's one thing that you cannot have in the denominator of a fraction. And if you think back to fractions, the one thing that you can't have in the denominator is 0. So the domain is going to be restricted by numbers that would make it so that this expression right here, the x squared plus 3x minus 4, is not equal to 0. So this is going to affect your graph because your graph is not going to have anything that on it in the places where there would be a number that would plug in for the x here and make this whole expression equal to 0. So first let's examine what those numbers might be. We're going to take this denominator right here and we're going to say that this thing here, the x squared plus 3x minus 4, cannot equal 0. Now, in order to determine that, we're going to solve this as if it was an equals, and the two values that we get out are going to actually be numbers that are not going to be okay for plugging into this function. So in order to solve something like this, we need to factor. And since this x squared right here, it has a 1 for its coefficient, we can look at the numbers that would multiply to get negative 4 and add up to 3. And that will help us find our factors. And if you think about it, if you multiply 4 times negative 1, you would get negative 4. And if you did 4 plus negative 1, you would get the 3. That makes it so the two factors will end up being x plus 4. The x is there because that's our variable in this trinomial. And the other factor is x minus 1. When you multiply these two things together, you cannot get 0. Because if you did get 0, the denominator of this expression here would be 0, and that's not going to be okay. So now, if you think about it, we have this factored, so we can use the zero principle property, where if you multiply two things to get 0 and you get 0, one or the other has to be 0. So that means that x plus 4 would be 0 if this became 0, which means in this case, because it's a rational expression, we do not want the x plus 4 to be 0. Or we could have the x minus 1 equals 0 to get a 0 in the denominator of our expression. So we want to know what would make those 0, because those are the things we cannot plug into the formula. So if we solve this, we would subtract 4 from both sides, and x cannot be negative 4. We would add 1 to both sides here, and x would not equal 1. Now, that means the two values we cannot plug into this formula are negative 4 and 1. Now, that also helps us find our domain, because our domain can be all x's such that x is an element of the real numbers and x is not equal to negative 4 or 1. That would be our set notation for our domain. Now, let's look at the graph and see how this affects the graph, and that might help us get interval notation for the domain. Our restrictions, if you were asked for what the restrictions are, that would just be the negative 4 and the 1. Those are the two numbers you can't plug in. So let's look at the graph in Desmos. Here's your graph in Desmos. Notice that I have typed it in here and I have a picture here. And notice that there is something kind of interesting on this picture. Let me change my color here so you can see it a little better. Right here, there's a line, and an invisible line. You can't really see it, so I'm going to kind of sketch it in, or try to sketch it in. And it's right here where x equals -4. This is an invisible line we call an asymptote that this graph actually never touches. So notice what happens is your graph is the red portion here. It has a whole bunch of values coming up from -infinity. So interval notation would have -infinity as your first thing going left to right. And then when it gets to -4, it doesn't touch this line that I sketched in there. So it gets up close to -4 but doesn't touch it. So you use a round bracket for that. And then you can kind of imagine we jump over -4. And then we start going from -4 up to here. And notice that there's another line that we go ahead and jump over. And that line is right here. That's another vertical asymptote right here. And that is at the value, if you take a look at the scale here, where x is 1. So we have values in here from -4 to 1. We don't touch the -4 or 1 because those are the values we cannot plug in. And then imagine yourself jumping over this line again and continuing from 1 and going off into infinity. So our interval notation you can get from going from left to right across your graph, and imagine yourself jumping over the invisible lines that we don't touch in the graph. Since we jump over those, there's gaps there, and we need to use union symbols for that. So that's -infinity to -4 union the section in the middle, which is -4 to 1, union +1 to infinity. So this here would be your interval notation, and if you wanted set builder notation for your domain, it would be this right here. Now, this was just one example. Let's see what happens in another example. How about these two? Now take a few minutes and pause your video. I want you to take a look at these two graphs in Desmos and think of what your domain and range should be and what the restrictions might be on that. Notice the asymptotes, when you do graph it, won't show up, but imagine those lines like I drew in on the last slide. Okay, let's take a look at the first one. One thing that you might have gotten when you typed in that into Desmos is a picture like this. Notice that in this picture there seems to be an invisible line we jump over right here. And that line, if you take a look at this, is at -5. There's also another one way over here. And that seems to be where x is 7 right there. So in interval notation, if you were looking at your graph, you would come up this direction, and the red part is the graph, so that is a section where we have a graph, which means you can plug these x values right in here in some from -infinity up to where -5 is. So we have a comma between those and a round bracket. Then you jump over -5, so we'll have a union symbol. And you go from -5 all the way up here to 7. So all these values in here. So up to 7 with a round bracket, union, and then you jump over 7 again, and you start here and continue off to infinity. So from 7 to infinity. That would be your domain on this graph. The restrictions would be the -5 and the 7. Those are the things you can't plug in. Now let's take a look at our equation here. If we were to factor this, two things that would multiply to get -35 and add up to 2, notice that that would actually be -7 times 5, because we need a -2. So that gives you a -35, and -7 plus 5 would be your -2. Notice those numbers are the opposite signs as what we have on the graph. The reason for that is because when you go ahead and factor this, you get x minus 7 times x plus 5. This expression here cannot equal 0. When you try to solve that, you end up with x minus 7 cannot equal 0. And you actually don't need the parentheses there. You can put them in if you want. You also end up having x plus 5 cannot equal 0. When you solve this, you add the opposite of the -7 to both sides, and you end up with x cannot equal 7. Notice that this corresponds to this asymptote right here, the vertical asymptote on the graph. Over here, if you subtract 5 from both sides, notice you get x equals, or cannot equal, -5. This corresponds to the -5 vertical asymptote at x equals -5 that we had on the graph. So it makes sense from the equation that the graph turned out this way. So now let's go ahead and I'll erase all this. Let's take a look at the second one. Something different happened on this second one, and we need to take a look at what's different about this second one. So let's get rid of everything I wrote here and take a look at that graph. Notice that there's only one vertical asymptote here. It's right here at 3. On this one here, there's only one, and it's right here at 3. But notice the denominator of this right here, it has an x squared. And if we were to factor this, this is a difference of squares that factors into x plus 3 times x minus 3. And that cannot equal 0. It seems that we should end up having two asymptotes, but we don't. The reason why we don't is because if you take a look at the numerator right here, this thing is x plus 3. It's going to cancel with the denominator, the x plus 3 in the denominator, and you're going to end up with a simplified expression of 1 over x minus 3. This is what Desmos graphed over here. So that's why you get only one restriction showing on your graph. You can't really see it, and it's almost impossible for Desmos to show it, but there's actually a little hole. If we were to solve this equation, we'd have x plus 3 cannot equal 0. We'd also have x minus 3 cannot equal 0. If you solve this, we get x cannot be -3. Your restrictions and your domain actually go back to the original equation. So we do need to take into consideration this one, even though it doesn't show up on our graph. There's actually a little hole right here on our graph. You can't see it. It's very hard. Even if you zoom way in, it's going to be very, very hard to see it. If we were graphing this by hand, we'd have an open dot at that hole there. And then this one here, if we add 3 to both sides, we get the one that still shows up, which is that x cannot equal 3. That's the one that didn't go away. And if you look at this denominator here, we would not be able to plug in 3. Our set builder notation for this, we would have x such that x is not equal to those. You would need to include both. Interval notation, you would need to recognize this removable restriction, the one that canceled out, and you would have to do -infinity to -3 union -3 to 3 union 3 to infinity. So you would need to go ahead and include all of that, because we would, on your x's, we would come up from -infinity, then we would jump over this hole, continue to this asymptote, then we would jump over the asymptote and continue on to infinity. And so that's what you need to consider on this. For range on this, if we take a look at the graph, one thing we haven't talked about is the range. On this graph, domain goes from left to right, this direction. But range goes up, down. If you go from the bottom up, notice that we have red all the way up until we get to the x-axis, and that's when y is 0. So right here we jump over what's called a horizontal asymptote, and then we can continue on upwards. So for your range, if we were going to do range, I'll do R with a colon to symbolize range. That would come up from negative infinity to 0. Then we would jump over 0, so that we'd use a union because there's a gap, and continue on from 0 to infinity, which is this section here because there's a red portion to our graph showing up there. You will only have to get ranges from the graph at this point. Set builder notation, range is a y, so we would have y such that y is not equal to 0 in this case on this graph. So, and that gives you a brief introduction to rational expressions and their domain, range, and restrictions.